Okay, let us discuss this problem. Problem number 1.251. So it seems to be an interesting problem. Let me first make the diagram for this problem. So there is a pulley, the radius is r, and this side we have a string that is having length x. So let us say what this problem says. So any form cylinder of radius r and mass m. So mass of this cylinder is m, capital M. Radius is r, capital R. Rotates freely about this horizontal axis O, so it can rotate about this freely, this axis about O. A thin cord of length L and mass m is bound on the cylinder in a single layer. So there is a cord that is bound over this, and length of this cord is L, that is bound over this, and this is bound in a single layer. This means I will have this cylinder is something like this. So this is bound in a single layer. So this is something like this. I cannot have layer over layer. So I cannot have one layer over the other layer, over the third layer, over the fourth layer. That is not the case. One in single layer. So I have something like this. So this cylinder has length of cord is L, that is bonded over this cylinder. So length of cord is L, and the mass of cord is m. So mass per unit length is m by L. So lambda is mass per unit length. So this is mass per unit length. Are you getting? So this is mass per unit length for the cord. Now next the question says, find the angular acceleration of cylinder as a function of length of x of hanging part of the cord. So we have to find what is the angular acceleration alpha of this as a function of x. X is the hanging part of the cord. The bound part of the cord is supposed to be center of gravity of the cylinder. The bound part of the cord is supposed to have its center of gravity on the cylinder axis. Now the bound part, this part that is bound, it can be assumed that it has also center of gravity at the center, geometrical center, that is the center of the cylinder. X part is hanging, and then we have to find what is the alpha as a function of x. It is easy. You see, now if this x part is hanging, basically x is variable. So what is the force that is acting? So you see, this part will have a mass lambda into x, because lambda is the mass per unit length. So lambda into x. So this will have a mass lambda into x. And the friction force that is gravitational force that is acting. So this part will have mg. Are you getting? And the mass is, I can work using the energy conservation, the same question, or I can even work using the rotational equation, writing the rotational equation. So let us try using the rotational equation. So what are the forces that is acting? So let us say this part of the thread, I make this thread something like this. So this is my thread. What is the downward force on the thread? Lambda into x into z. Lambda into x into z. That is acting in the downward direction. Let us say upward you have a tension T at this point, because tension will also be varied. Let us say at this point, you're getting at this point, tension is T. So now I can make for this pulley, I can make the free body diagram. At this point tension is T, because I can assume at this point tension this side and tension on this thread and tension on this pulley will be same. Now let us say this is going down with acceleration a. So this will also rotate by acceleration alpha, and this point, now I can say, if I consider this point is a part of disk, so acceleration will be alpha times, so linear acceleration of this point is alpha times r. But the linear acceleration of this point is also given by this point. This is a. So I can say A is equals to alpha r. Because linear acceleration of this point either I can give from disk or the cylinder, and if I consider the disk, linear acceleration of this point will be alpha times r. Now if I consider this point here, linear acceleration should be A, so I will have A is equals to alpha. This means this point will have acceleration A is equals to alpha r. So acceleration I can either find using the rope or I can find using the cylinder. Now things are easy. I have to simply write down the equation. If I write equation for this, so lambda xz minus t is equals to mass into acceleration, so mass is lambda x into acceleration. Now if I write equation for this, so torque is T into R is equals to I alpha. Now the disk will have mr square by 2, but I have a thread, and thread will have, so total length is L, so on this bonded length is L minus x. If I multiply by lambda, so this will give the mass of thread that is over here, and if I multiply by r square, this will give you moment of inertia. So moment of inertia of thread that is bonded here, I can write lambda L minus x into lambda into r square. Let us try to understand this one. So this is your pulley, and there are some thread that is bonded here, and the thread have a length that is bonded is now L minus x, because x length is hanging. So if this length is hanging, so rest length is L minus x. Now these all points, these all threads are basically at a distance r from the center. So the moment of inertia of these all points, that is the point of thread, will be mr square. So if I add all mr square, so this becomes the total m. The total m is L minus x lambda into r square. So this is my equation number 2. Now I have to solve those equations. So even this is I alpha, so I have to multiply by alpha also, and alpha is basically nothing but A by r. So I have to write here A by r. So alpha is equals to A by r. I can modify equation 2, so I can do some more massaging. So this r goes, so t is equals to r here m by 2 plus L minus x into lambda. Are you getting? And this multiplied by A. So let us write A here. Now if I plug the value of t in equation 1, so this is my equation 2 in a modified form. So from 1 I can write lambda xz minus, tension is this, A times m by 2 plus L minus x into lambda. This is tension, this should be equals to lambda into x into A. So basically now I have to solve for acceleration. So if I solve for acceleration, I will have, so let us say lambda xz, this is equals to, now I have to take A common, so I will have m by 2 plus L minus x lambda plus x lambda. Are you getting? Now x lambda goes out, so we will have lambda xz, this is equals to A m by 2, and this x lambda goes out, so we will have simply L lambda. And L lambda is nothing but mass of this total mass of cord, that is m. So this is simply lambda xg is equals to A m by 2 plus m. So what is the acceleration? So acceleration is lambda xg divided by m by 2 plus m. So this is the acceleration we have in this case. And if you want alpha, you have to simply divide by r. If you want, you can replace lambda by m by l. So lambda is nothing but m by l. So I can also write the answer in terms of m by l. So this is m by l, m by 2 plus m into x into z. So you can write the answer in terms of, or you can more modify if you want answer as in book form. So you will have 2m xz divided by l m plus 2m. Are you getting or not? So this is a fairly easy problem. One important thing you have in this case, you have to consider the mass of thread very carefully. So what we have said is, we said the rope that is hanging will have acceleration a, and I can write equation of motion because the mass of rope that is hanging is lambda xg. It has acceleration a, and tension in the upper point, tension in the rod, tension in the cord is varying, but the upper point I can say that the tension is T, and the same tension that can be applied on the cylinder also. So now I know the tension on the cord, I know the tension on the cylinder. Now I can write down the two equation of motion. Equation of motion for cord, equation of motion for cylinder. And another important point is, in this case also again, you will have A is equals to alpha r, because this point, if I consider this point will have acceleration A is equals to alpha. So linear acceleration of this point is alpha into r, and this is the same point here. So this point also have alpha r into acceleration. So I can say A is equals to basically alpha r in this case. Are you getting? So this is a pretty easy problem. If somebody has missed something from here, you can copy and then we'll discuss the next problem. So pretty easy problems. Basically you have to be master of rotational equilibrium questions. These are the easy problems. If you see the JEE questions, even they are asking tougher questions than this. They apply more concept in the same problem. These questions contains very simple concept. You have to apply torque is equals to I alpha r, and you have to apply A is equals to alpha r. But if you see the JEE questions, they apply more concept in the same question. They have A is equals to alpha r. They have how to find moment of inertia using the parallel axis theorem or perpendicular axis theorem. Even they apply the momentum conservation and angular momentum conservation in the same problem. We'll discuss sometime. In one question, in earlier days, they have asked in a single question there are so many concepts that is involved. So you have to try those questions that have many concepts in the same question. Are you getting? And that will give you idea how to solve the problems easily. And problem solving is again an art. You can learn only solving problem by solving problem. There is no any other way. Even today we are doing so many problems, but if you give some new problems, I have to think. Maybe I will not be able to do. Even teacher will not able to do, because you have to keep practicing. If you have seen those kind of concept, you can easily bomb it on the paper of exam. If you have not seen that kind of concept, it is very difficult to solve those questions in exam. Of course, you can solve at home. You can take time, you can solve. But in exam, the only concepts that you are going to solve that you know exactly. Okay, we'll discuss the next problem.